chancellor for research here, and I thank everybody for coming, and thank Leroy for putting this together. I think it's going to be a really interesting presentation. Professor Hulsey has quite a distinguished background and quite a lot to describe. So I'm going to try and briefly describe some of his accomplishments. First, a brief introduction to the University of Alaska at Fairbanks. So we are really, we have our niche, we have our specialty in cold regions, science and engineering. And the way we've really developed strong engineers in cold regions is to develop good engineers. And the way we develop good engineers is to hire the best engineers we can. And we've got a great faculty here, and I think that the results of the great faculty are the very prolific and capable students that we've produced. So Dr. Hulsey he's been a longtime member of the Civil and Environmental Engineering program here. He's been the department chair several times. He's became a professor here in 1987, and he's had a very prominent role ever since. He's been engaged in engineering and teaching and research since then. He has extensive university and corporate experience. He's owned and operated and ran 3 high-tech engineering research companies. He has extensive teaching and research experience at the University of Missouri-Rolla, at North Carolina State University, and the University of Alaska Fairbanks. He's been in active research and has served as department head and participated in many university committees. His expertise is primarily in mathematical modeling using state-of-the-art methods in finite element, finite difference, and theoretical solid-state mechanics. His research is in the fields of bridge engineering and the effects of temperature extremes on structural systems like composite wall panels for buildings. His primary focus has been on working with students to achieve a high-quality education, and I think we can really credit him with the number of great structural engineering students who have come out of here with who've gone on, who give their credit to and thanks to their start for Dr. Hulsey. So Dr. Hulsey has also mentored our steel bridge team for over 2 decades and has led them to 1 national championship and several top 10 finishes. UAF has placed in the top 10 teams at the national championships during 6 of the past 10 years, and that's an incredible accomplishment. So 6 of the last 10 years, UAF has been in the top 10, and that's out of about 250 teams nationally. So we're taking on teams like MIT and Berkeley and doing just great. So in 2015 at the regional team, I want to point out that the UAF Steel Bridge team won all 6 categories: construction speed, lightness, display, stiffness, economy, and efficiency, and the regional title, and went on to place 9th nationally. So I mean, we have wonderful students, incredible capabilities, but they get that talent and that background from great professors such as Professor Hulsey. Professor Hulsey has also been involved in forensic engineering. He's been a consultant and a researcher to several notable bridges, such as the Yukon River Bridge, the cable-stayed Skagway Bridge, and the $1 Million Bridge, which these days would probably be a footbridge. But, so Professor Hulsey will make a presentation, which will be about an hour, and we'll take questions after that. And so I will thank you very much for your attention. Professor Hulsey.
Thank you all for coming. I really consider it an honor to have the opportunity to share with you today some of the work that we've been doing over the past 2 years. And I'm just delighted to have been asked to be part of this study that the University of Alaska Fairbanks has been asked to do. It's a very prestigious opportunity for us to share what we have in terms of our knowledge about this particular structure. So today we are going to be talking about a structural reevaluation of the collapse of World Trade Center 7. What makes this is interesting in many ways is World Trade Center 7 was not struck by a plane. It was a part of the complex and yet it failed in the afternoon. So the National Institute of Standards, NIST, issued a report in 2008 which concluded that the structure collapsed because of fires causing the floors and beams to expand due to high temperature, due to fires, triggering a series of structural failures that then culminated in the total collapse of the building. Others have argued that that fire was not the likely cause of the failure, and there's all kinds of different discussions about what may or may not have happened. So I want to make it real clear here today what we did and the way we approached this. This project was undertaken to answer the question, did fire cause this building to collapse? That's our focus. So we have been very careful to let the science take us where we need to go. Never once did I want to hear or understand where all these different possible views might be, being a very controversial subject. So I tried to make sure that at the end of the day, every day, that the decisions that we were making, the arguments that we were putting forth were defendable purely through science. And so that's what we believe has come out of this. Through that process, if I may back up for just a moment, through this process, I was the director of this research. I was fortunate to have Dr. Fang Shao, who is now at Mississippi State, I think it is, or down in the South. He's a postdoctoral researcher there, but prior to coming here, or leaving here in December, he was a researcher on this project as well as working on his PhD under me on a project dealing with structural health monitoring of bridges. I'm also very honored to have Zilli Kwan, our PhD student here at the University of Alaska Fairbanks, who's been working with me from the day one on this. And Zilli, I'd like for you to stand up for just a moment and be recognized by the audience as to the fact that he's been participating. And without their help, it would have been extremely difficult. So I'm just really honored to have that kind of talent working with me during this period. Let me begin by saying, before I get any further, that we are going to, this presentation is basically a September 2001 progress report, a September 2017 progress report. Almost everything is almost complete except for one thing, and that is the progressive collapse of the structure. We have been working on that for some time. We are very pleased about its progress, but there's many things I want to look at yet. And so today I won't share that with you. And when we get close to that, I'll show you what you might be expecting in the future about this and why I'm reluctant to share it with you today. More importantly, I want to let you know that what we're going to be putting out today is, since it's a progress report, this is not a traditional slideshow where I have just bullet points. There's some here where I have quite a bit of prose. And the idea is that this will go out and make it available for you to read additional information if you would so choose to do that. We're going to be transparent. We welcome any questions. We're making everything that we have done available so that we want to make sure that everything that we have done is scientifically tested. So we'll have a peer review committee to make sure that we've met all those standards. The methodology. Today, the methodology, I want to share that with you. We assembled first the available documents, direction drawings, etc. that were available for this project, for this building. Traditionally, I would have liked to have had the opportunity to go in and pick up all the pieces of the puzzle and put it back together like you would a typical airplane. They did not exist. It wasn't available. So we've done the best we can with all the available documents, and basically what we did is create an AutoCAD drawing here that we used it to create a virtual geometry of this 47-story building. Basically, in digital form, you should be able to see every piece, every puzzle, every member, and it should look exactly like what was used in that structure. And so that's what we did. We then prepared an abacus nonlinear computer model for the connections and for the framing of this building. And so that is a fairly sophisticated finite element program that's available that enables you to look at in the detail how something is going to respond under a set of conditions. So I know that I have a mixed audience here. I'll try to keep it as simple as I can. At the same time, I need to share with you some pieces of complexity so those in the technical arena have an appreciation for the fact that, okay, so they did look at this
in a fairly sophisticated way. We've taken there's several things here that I haven't talked about. We have Sept 2000, the current editions, version 18, and Abacus, and we use that to look at the framing. And so in the plan view, when we were looking at a microstructure, we were using both computer programs and two different people, and each one of those PhD student, PhD people that were working for me, they were doing these individually, and I was there to quality control, ensuring that everything was the same. And were we getting the same answers from two different approaches, two different people doing things? So we had a quality control assurance. This is a highly complex system. So we want to make sure that at the end of the day, we were getting reliable results, and we could test it against more than one way to do this. So we looked at the framing at floors 12 and 13. They were modeled for fire damage. This is in the plan view. I'll go through this. I realize it's not clear to you at this moment. So I'm going to give you an overview, then I'm going to tell you what we did, and then I'm going to tell you that again. So Sept 2000 and Abacus was used to study progressive collapse. We are using it to study progressive collapse. I'm not done with it yet. So that's not what I'm going to share with you today. Basically what that means is that at the end of the day, you look at the side of the building and you see it come down. Does it look like what actually happened? And that's the place where we are with that, okay? Virtual structure was used to simulate the conditions on September 11th, 2001. Then we're going to share with you the findings, and this is going to be peer reviewed. So the findings to date, part 1, WTC 7, World Trade Center 7 building was not found to be collapsed by fire. That's my conclusion. That's what we found, okay? That's not consistent with the findings that were previously found by others. Findings are based on results from this Abacus and Sept 2000 model. Part 2, progressive collapse analyses are nearly complete, and we're using Sept and Abacus for evaluating that. I might point out also we've used SolidWorks and other procedures to look at fire-related issues, and I haven't provided that information here. So I want to acknowledge and thank the funders, who are the architects and engineers for 9/11 Truth, and they are funding this University of Alaska Fairbanks and the Institute of Northern Engineering and the College of Mines to do this work. It should be pointed out that this is a non-for-profit corporation, and the money that came to this study was out of the pockets of those professional engineers and architects. It was donated. So this was something that I think is pretty significant. Let's talk about the building for a moment. We have an obituary for this building. 1983, it started. 2001, it left us. The height of the building is 47 stories, and an emery cloth and Sons design with a red granite facade is what it looked like. The geometry was a trapezoidal footprint, which we'll see in a moment. 610 feet tall, kind of gives you an idea about how tall it is. 330 feet long and 140 feet wide. So the construction began in 1983, and it was opened in May 1987. Please share with me if I'm moving too fast or if I'm moving too slow, and I'll gauge ourselves as we move through this, because I have a lot of information to share with you today, and I understand that you're not going to absorb it as quickly as I would like to see you absorb it. So you need to kind of give me some input back. Anyway, so the foundation, the building was constructed on caissons. It was actually built above and through a 1967 Con Edison substation that was designed to carry a future 25-story building. However, when this building came on, there weren't enough caissons there, so they've added caissons, and they were to the proposed support system, and so this was the foundation for this building. The structure, basically, here's the concept. The structure is a system of gravity column, transfer trusses and girders were located between floors 5 and 7. I'll show you that in a moment, give you clarity to that. The 5th floor functioned as a structural diaphragm, providing lateral stability and distribution of loads between the new and old caissons. So imagine down at the bottom at the 5th floor, you had these irregular conditions going on, and that structure portion took care of that. Above the 7th floor, the building structure was a typical tube frame designed with columns in the core and on the perimeter, and the lateral loads were there to resist, and lateral loads were resisted by perimeter moment frames. Okay, so please bear with me. I understand that some of these words You're going to understand, some you don't, and I will try to my best to get you there. Let's just take a moment and take a breath of fresh air and remind ourselves that we're now looking at history. And in this history lesson, we are seeing the WTC complex, World Trade Center complex, that disappeared in 2001. And in that, and happened to be on my wedding anniversary, by the way, which was not a good day. It was and it wasn't. You know, certainly this was the most god-awful thing that ever happened in the United States. Certainly one of them. So here's the Twin Towers, WTC 1 and WTC 2, and over here is WTC 7, that kind of a brick-looking facade that I was telling you about earlier. Kind of a beautiful building, located about 350 feet north of World Trade Center 7. In other words, about, what, 300, what is that, about 100, little over 100 yards away. World Trade Center complex elevation is what we're looking at here. That's what it looked like prior to September 11th. In plan view, it's going to give you a different perspective. Here's the north arrow. So the northeast corner is where our day is going to, we're going to spend our life in the next hour in that northeast corner. That's the farthest way from that arrow, okay, of that building. That's plan view. This study is really about why it came down. This building was not struck by a plane, yet it collapsed. That's almost an overwhelming thought if you stop to think about it for a moment. If we're looking at it from an elevation view and try to take a look at the very sides of this building and what it may have looked like. Here's the north elevation. So when I talk about the north elevation, I'm really talking about this elevation here, the width. Notice that it's wider trapezoidally than this south elevation. So the building is not symmetric, for God's sake. I mean, so there's all kinds of issues. But this makes it really interesting. And so here's that width. So here is the south. Notice it's not as wide. And then here is the west elevation and the east elevation. Now within that context, here's 413, because that's where I put that there, because we're going to spend a lot of time there. So you'll have some understanding of what the heck's going on in that area. Here are these perimeter trusses I was telling you about. That's at floor 5 and 7 and 24 and 22. Okay, those trusses are resisting lateral loads. And then so in the plan view, you see A, C, D, and so forth. There's that building in plan view, and here's what we're looking at. And down below here is the Con Edison substation, shipping, so forth, all the things going on down there. Okay, so that's what it's built on. That's what it looks like. That's what we're dealing with. Way more complex than that. That's the perimeter view. That's not what it looks like in the internal view. Oh my God, here's the internal view. So all of a sudden, we see that there's a plan view, there's frame, there's structural systems everywhere. You know, and so these little hexagons are the columns. The supporting vertical loads. These other things are either girders or beams. So the main core carrying members, like this right here, that's a girder. These things framing into it are beams. So this girder is an A2001 we're going to talk about. We're going to talk about girder A2002. This is column 79, where we're going to spend quite a bit of time this afternoon having a conversation. This is a beam on the exterior, G3005, and the reason it's important is because it has to do with the lateral bracing of this whole system. I turned these things in circles because, again, they could have been hexagons, but I wanted to bring them out so we could pay attention to them. And that's column 44, column 79, column 80, and column 81. And then it's column 76. So our life in plan view is going to be in that area. Because column 79, just to give you a snapshot of where we're heading, column 79 it basically is what they said failed to bring this building down. So we're going to go there and take a look at it. And we're going to look at it intensively. So what were these crazy fires? You know, they started, keep in mind, I should have had a slide in here, I suppose. I thought I did. About when World Trade Center 1 and 2 actually got hit. That's in the morning. And then later in the afternoon, World Trade Center 7 came down, hours later. And they had fires that were reported having come from World Trade Center 1, coming through the windows and so forth. And they were on floors 7 to 9, 11 to 14, 19, 22, 29, and 30. And this is after the NIST report, where they were reported those fires. 1 hour before collapse, it's reported that there weren't any fires on floors 3, 5, and 7. So there were fires up in here. Question is, you have to ask yourself a lot of questions, and we don't always have answers. Okay, so where's the combustibility? This is a steel structure. So what actually was going on in this building? And we'll get there shortly. Okay, so did WTC 7 collapse from fires? And our study shows the fire was not the cause. Now, I'm not going to tell you about what did it. I'm just going to tell you that it wasn't that. What I am going to do is, maybe not today so much, but a little bit later, when we look at the progressive collapse, is tell you what had to happen for this thing to come down. Okay, that we will be able to tell you. This contradicts findings presented by NIST. Our presentation will address this issue. We will discuss the NIST approach and our approach and findings. So what's next after today? We'll have a progressive collapse analysis are ongoing, and when we finish that very soon, we'll make that available to everybody so you can see it. I wanted to have them today, but I'm not going to give you something that I have to change later and thinking, oh my gosh, I rushed it and it was wrong. I'm not going to do that. Okay? I would rather give you something that you can feel comfortable with when we're done. So the NIST assumptions and claims that were used in our in the UAF analysis, let me kind of give you a snapshot here where I'm going with this. NIST had some assumptions and claims that they used to get that report, to come to the conclusion they did. So what we've done is several things, and I meant to put this on a slide. There weren't enough nights in the day to make this happen. So this one slide I'm going to share with you verbally. So basically, the NIST assumptions were what I'm laying out here. We then did several things. Number one is that we looked at, could that have actually occurred if we used their assumptions? So that's one thing we did. The other thing we did is we simulated exactly what they did to see if we came to the same conclusion. And we did that by several things. Number one is that this World Trade Center building is a steel frame structure with steel beams, steel girders. Does everybody have an idea what I'm talking about when I say those things? It's basically supporting a concrete floor. That concrete floor is supposedly to be fastened to those steel beams and steel frames using what they call shear connectors. In other words, those are round bolts that are actually welded to the top flange. And then when you pour the concrete, it all becomes one. That was the concept, composite structure. But there's so many questions concerning this system. We looked at it from composite, partially composite, non-composite. That means the slab can slide over the steel, not slide on the steel, partially slide over the steel. We looked at all those possibilities. We looked at whether the fire was underneath and burning up the ceiling, or looking at it and burning down the floor. I mean, all of those issues were examined. Here's their assumptions. The beam temperatures reach 600 degrees C. The girder temperatures, A2001 and A2015, reach 500 degrees C. Okay, so what am I talking about here? So let me go back for a moment and share with you. A2001 is that girder. A2015 is, right here, okay? So these girders are what we're talking about in that temperature range, okay? The beams didn't get that hot. Okay, so if we take a look at, when we take a look at the beams, they reach 500 degrees C, and the column temperatures only reach 300 degrees C. Now that's significant, because there's a point in time, and I'll show you a moment, whereby there's a point where the steel begins to decrease in strength and modulus decreases when you reach a certain elevated temperature. So the first thing I would have thought about when I got involved here is, okay, the columns obviously got really, really hot, and they lost strength, and we would have ended up losing the building. Nobody seems to think that ever happened. Furthermore, there weren't a lot of combustibles in there. So no east exterior wall deformation occurred due to expansion of beams. That's their assumption. In K3004, C3004, da 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 da. Where's that at? Just to kind of give you a heads up on what I'm talking about, that's along this line. Okay? Those are the lines of these beams right here. You see these beams? They're going into these girders. They're framing in. Am I making myself clear? So in plan view, I've got a beam going from this outer edge to that girder. And those are beams. And those are the numbers, 3004 and so forth, that we're talking about. Okay? All right, so now moving on with that idea in mind. We've got all that beautiful thing captured in our minds. We're ready to go. So there were no shear studs were installed on the building girders. So I'm going to take you through where we disagree in a lot of areas. Shear studs on beams K3 and K330. These beams, by the way, these beams, they're saying the shear studs on those beams were broken. The bolts fastening girder A2001 to its seat at column 44 and 79 were broken. That's significant. So let's go back here. Here's 44 and there's 79. And they're saying the connection of this girder to those beams, to those columns, the seat connection, did not function during that period and therefore lost support, lateral support, and produced a problem. Okay? So, going backwards here or something. Hang on a second. I'm going crazy. Too much fun. All right. So they've lost those supports. So that means those two columns no longer have lateral support at that level, and did they possibly have a problem later? The floor loading was 88 pounds per square foot. The NIST computer model results were based on exterior columns being fixed in every direction. That's kind of a significant thought. All right, so now, looking at their plans, this stuff, this came out of the NIST report on page 343, 2008. And so this gives you a geometry of, that's a 44-foot length from 44 to 79. 44 foot, that's a girder length. 44 foot, you know, that's longer than this, for sure. You see what I'm saying? That's not small. This is a huge building, 600 feet across. I mean, for God's sake. So here is, 50-some feet here, 54 feet across. This is our exterior wall. I'm in the northeast corner of this building. Is that clear to everybody? That here we are in that trapezoid world we are. Notice that there's axisymmetric framing. These beams, those beams, for God's sake, are 52 feet long. That's not small. I mean, where in the world do you see that kind of stuff? So anyway, so in their view, by taking a heat model, putting fire on it and then subjecting their model, their finite element model, to a increase in temperature, they got a thermal expansion. Their thermal expansion looks like this. So that actually is this girder right here, A2001. It expanded, and they said it pushed off of this seat, bearing seat, and thereby they lost support. And then these cascaded downward. Okay, so that's basically what we're talking about here. There's that girder I'm talking about. There's that exterior. And here are lateral supports for this beam system through here. So what were their conclusions? First of all, their fire-induced weakening of critical columns did not cause the WTC7 to collapse. Okay, didn't get hot enough. They're saying that 300 degrees is not hot enough. No argument. Temperature in column 79 was below 200 degrees C. I think that's true. I might have to look that up as a reference again, but I'm pretty sure that's in about what it was. Movement along the axes of beams K304 to 3005 was caused by thermal expansion. Then the lateral displacement of the girder framing into column 79 was a result of thermal expansion of the beams framing into the girder. All we're saying here is when these heated up, they got longer. This was fixed, so they're all going to move to the left. That means they move what direction? West. And in moving so far west, what happens? Well, they're going to try to move, and is there enough space to hold them in place? That's what their argument is, right? That's key right there. And that's what it looked like. Bang, 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 right? This thing bowed outward. And so this moved and that moved. Okay. This is the cascade issue that they said. Okay, so the buckling initiated here at this place right here, at floor 9. And then all these issues means that they lost lateral support of that column. This is column 79, by the way, the one I'm talking about, the one we've been focusing on. That column 79 is, okay, so it doesn't have any lateral support, and because of that length, it cannot take nearly as much load as it was designed for. And so consequently, the vertical support and lateral restraint in the north only, and so therefore there's a huge problem. And then there's full lateral support up here, and then there's partial lateral support down below. Okay, so that's down here in the bottom, down here at the very bottom in the kind of Edison area. Those are all laterally supported. So, but between this zone, they said, went away. So the loss of lateral support for 9 stories, floors 6 to 13, caused buckling to initiate, which means you lost it. Okay? Is that clear? Everybody clear about what I'm saying here? Okay. Now let's take a look at their model for a moment. Their model is, this is looking at a partial of that trapezoid. Down here, partial. We're seeing a partial of it. This is the northeast corner. There's column 79. And in that blue, it's kind of significant. That blue is where they put, at every place a beam and a girder come together, a column to girder goes together, a beam to all these kind of things. There's a connection that's on the drawings that says, here's how you will build it. You bolt it together, you make it do whatever you want it to do, and that's the way it was supposed to be built. Remember that the north arrow is here, this is the west side, the east side is to my right, and so, and this is after NIST, the area of floor where connections were modeled on floors 8 to 14, and that's in the blue area. Over here, that wasn't done. So, there's column 79, here's the area outside of the thing, and so now let's take a look. Outside the selected area, connection failures were not modeled. NIST used fixed or pin connections. So automatically, you have to ask yourself the question, do they have the same stiffness as what you were modeling here more accurately? And does that and so the next corresponding question is, does it have an influence? Does it change how the system is going to respond? And so the connections were not modeled for the exterior frame, and the columns themselves were treated as fixed. So also in the NIST documentation, page 525, 2008, a girder was considered to have lost vertical support when its web was no longer supported by the bearing seat. That means the girder. That means if they're lost of bearing support on A2001 coming into the column 79, then it's lost. The bearing seat at column 79 was 11 inches wide. Thus, when the girder end at column 79 had been pushed laterally at least 5.5 inches, the web over, it was no longer supported by that bearing seat. NIST changed that 5.5 inches to 6.25 inches when it was shown that the seat was actually 12 inches wide. So that's kind of something to think about. Why did that happen? And that was later. So some of the NIST results are the following. And pardon me if I'm just kind of, I hope I'm not boring you, but so this is a passion for me. But here, let's just kind of take a look at what actually happened. Here's the NIST model. And remember those connections that are, okay, so we're looking at this not from the south, we're looking at from the north, right? And isn't that right, Zilly? Or am I looking from the south?
Yeah, that's north face of the building.
Yeah, exactly. North face of the building. So here's a penthouse up here, and here are the, you're going to see two different situations here because of the connections issue. Now let's see what this thing, and this is the real building. So here's their model. This is their progressive collapse, which I'm not going to show you ours yet. And here is this one, okay? And here is taking a look at the failure. Actually, that did occur that day. So one has to ask themselves, is that the same thing? Is that the same building? So it looks like it behaves in an interesting sort of way. Okay, so anyway, let's go on. Here's the NIST model that we were just looking at. And here are, so this is the other side, you see, flipped, that I'm showing you where that modeling was actually done. This is column 76, 78. And so in 79 is in here. And so they were looking at this finite element progressive model that they were using to look at that. Well, I suppose we could even look at it from a different perspective. And there it is again. This is what they're doing. You have to ask yourself the question, though, is why is it so much different on one side than the other? You see what I'm saying? And here's things that they, because of some damage that came in from the debris falling through the windows and stuff, they're accounting for some of that stuff. Anyway. All right, so let's talk about UAF for a moment. Analysis of the NIST collapse initiation, hypothesis and propagation claims is really what we're about really to embark upon, is how valid is some of this stuff from a science point of view. So UAF analysis of the NIST collapse initiation, hypothesis and propagation, we created a solid model, an abacus, of the structural members in the northeast corner of the 13th floor of WTC 7, and a finite element analysis was then performed to replicate the results claimed in the NIST WTC 7 report that girder A2001 was pushed or rocked off its seats at columns 44 and 79 to initiate the collapse of the building. So one might argue that if those things didn't happen, would the building have collapsed? So, okay, so here we go. This is the area I'm dealing with, right in here. There's column 79, there's that girder, A2001, there's 44 and 79. And the question then becomes, how does it behave? So what we're going to do is we're going to create part of a finite element model, and we're going to be really conservative. We're going to force things to happen that's worse than the real world, okay? And in so doing, if we can't force failure, then it couldn't have happened. Are you with me on this point? All right, so that being said, we're going to fix the ends. We're going to force movement through girder A2015 by heating it up. This over here is going to be heated up. These beams are going to get heated up, and they're going to be fixed in the other direction. So we're pushing it each direction, making matters really, really the worst possible. And this is what that model looks like before it gets run. So we don't have the entire floor system here. We do, by the way, have entire floor system. But for this analysis, to evaluate what's going on right here at column 79, that girder, this condition, we're looking at what we need to do, and that is look at the boundary conditions to force that condition to be absolutely the worst possible. Okay? We did that. And so this is the beginning. You'll notice everything's zero. The stresses are all zero. We haven't put the temperature on it yet. Okay? This is the column that we're talking about. This column 79. This is real significant, by the way, because column 79, if you look at it, do you know what I'm talking about when I say a W shape? W shape looks like an H. And that's what we're looking at right here. That's what that column was made out of. It's a W14 by 730 standard structural shape. What that means is it's 14 inches deep, weighs 730 pounds a lineal foot. That's a chunk of change. Now within that context though, what they did is they built side plates on it. And they closed that box. They closed it so it has structural integrity, so a resisting twist, significant. But those edges, those 2 inches by 26 inches buildup, means that there is a lip on each side of this, and they're going to literally put on that flange the bearing plate. Okay, are you following me? We're going to turn, that column stays vertical, but we're going to put a bearing plate in here. Okay, so there's what it starts to looking like. We're looking at it right now. Plan view, A2001, going over to 44, and there's a connection to column 79. And see that lip right here? Those lips? Okay, got it? Understand? So if this thing starts, if it starts moving, and it's getting shoved, and if it's getting shoved to the west, which is to my left, it's probably your left too, then it's gonna, it can't get past that thing. Unless something happens or breaks, right? Does that make sense? And there it gets shoved. So the plan view of A2001 moving across its bearing seat at column 79 due to thermal expansion of the beams framing into the girder from the east is here, and it gets shoved. Note that picture illustrates that A2001 is A2001 is trapped by that column side plate, and it's not possible for it to move the girder web beyond the seat claimed by NIST. They're saying it got shoved off and fell down. The fact of the matter is they didn't have the side plates on it. They weren't there in their model. So they wouldn't have found that. But yet they did exist in the structure, in reality. It appears that NIST did not examine the side plate influence on the restriction of movement by that girder. Okay, so now let's take a look at what else we looked at. And this is just part of the puzzle, because we've been playing this game for 2 years. So this is just a few weeks of stuff. So the model shows the influence of the thermal expansion at the northeast corner of floor 13. Here we are. There's column 79, column 44, and there's the northeast corner. And here are the beams framing in to that girder system. So when girder A2001 is trapped behind the side plate on column 79, these beams begin to buckle. In other words, they can't go in here. So it's heating up, it's pushing, and they can't stand the amount of load axially that's been imposed upon them. And so they begin to try to displace out of the way and relieve them their states of stress. Are you following what I'm saying here? So fundamentally, that happens. So this is out of the NIST WTC 7 report, figure 8-22, which is showing basically concrete slab, metal deck, all that kind of stuff. Exterior columns out here, and this is basically column 79, column 44, and how that column is, and the girder here, and so forth, okay? And here's what begins to happen on the exterior columns according to their stuff, okay? And so they did not have that, those side plates in there. So let's treat for a moment the lateral support beams, S3007, and so here we are in this area right here. See those little beams in here? They play a role, and that means that they provide lateral support for that beam. They provide lateral support for that beam, also for that exterior. So they're forcing them to act together, not as individually. So if things actually got out of hand, you have a lot more capability from a lateral torsional buckling point of view or an axial load point of view. And so the lateral supports on us were left off in G3005, okay, of this beam. They were left off. Those were left off. Yet they're there. So that means that something could happen, and there it is. So the UAF analysis showing beam G3005 does buckle when lateral support beams 3007 spanning to it from the north exterior wall are not installed. Okay? So if those are not installed, it's going to buckle. Okay? So the UAF analysis also shows that that girder does not buckle when you have them in. There's a huge difference between those two thoughts and what that might mean to the behavior of this system, spanning to it from the north exterior wall as we see here, okay? So as everybody getting a mental picture of this building, you should be almost getting an intimate view of what we've been living with in this picture, okay? Let's take a moment, take a breath of air, Section of view of actual configuration of girder A201 at column 79 from the Frankel 1985 drawing 9114 showing there's partial height stiffeners in here. Now, folks, let me just absolutely tell you, this is critical. Those stiffeners prevent this buckling, this web from buckling. But more than that, it prevents these flanges from getting over stresses and flexurally having a problem. If they're there. If they're there. But NIST did not include them. So, partial height webs are missing. That means there's some issues here that we literally affects the behavior of this system. So figure 823, phenomenal analysis from the NIST WTC 7 report, note partial web stiffeners are missing. So the behavior of this interaction between column 79, A2001, column 44, the beams to the girder, the moving of the girder on that bearing stiffener, I mean on the base plate. Now remember, they didn't have the base. They didn't have the side plates. They didn't have the stiffeners, and all of those things are going to give you a huge added resistance to anything going on here. And in spite of the fact that I'm going to share with you some other things that makes it quite interesting. So here we go. There's what if you don't have any side plates. So the analysis was performed forcing girder A2000 beyond its bearing seat by removing the column side plate, increasing the coefficient of thermal expansion of the beams, framing into it by 40%. So we could get that kind of movement. That's not true. We did it just to see what could happen. Without the increase in the coefficient of thermal expansion of the web, would not have moved sufficiently to get it off the bearing seat. We wanted to see if we could make it move. Okay? That's what we did. That's at column 79. That's A2001. Is that clear? Everybody got a mental picture of what's happening? Well, again, this is the UAF analysis shows that the girder will not fail with the partial height web stiffeners installed. That small area of high stress is not in the load path, right here, right there, is not in the load path. That's a point of high stress, by the way. Is not in the load path, and it's due to the tip of the girder being compressed against the flange of column 79. This is not a structural concern. It's a fact that there was some overstress there. Oh, so it. It's not going to cause the building to come down. So we also conducted a modal analysis showing the 52 Hz frequency mode of the falling beam and girder assembly, which was needed to calculate the combined stiffness of the contacting structural members and the subsequent impact load on the girder below the 12th floor. So here we are on the 13th. It falls, drops off of that base plate, drops down, beams go, girders go, concrete goes, all that stuff happens. You're going to have stiffness involved. You're going to have F equals MA involved. You're going to have those conditions. And so we looked at that. The NIST and ARP claimed that the falling beam and girder assembly from floor 13 impacted and broke through floor 12 in an 8-floor cascade. Okay, so based on the natural frequency of the stiffness of the beams can be calculated and the amount of deflection of load can be examined. This establishes whether the phenomena could actually physically occur. I want to just share with you, I'm not going to spend any time on it, but those calculations are in the following pages, okay? So we did that to examine that issue. And that's where they are. You can go, at night while you're relaxing, you can read these. So, but I'm not going to read them for you. So anyway, so we had this 215,211 pound impact force is only 34% of the 632,000 force required, and thus insufficient to shear the girder bearing seat wells, and the southeast corner floor 12 would not have collapsed if a girder at floor 13 came off its seat. That's basically what we're saying. Thus, the ARP analysis did not show a base for propagation, even if the girder were to fall off its seat in column 79. These findings illustrate the ARP's explanation is actually invalid. That's another group, by the way. So there's more than one group involved. Weidender's associates report this information is going to be presented a little following this, and so here that is, if you want to read it. And I originally had a change to this, and it looks like that change didn't get made, but I broke this out. So anyway, let's talk now about our approach, which is looking at things from a different perspective. There was a 5.5 inch movement at the girder bearing support column 79 according to the NIST. The issues that led to that 5.5 inch movement was non-composite at the main girders. Now, what do I mean by that? So you have concrete floor slabs, and on those concrete floor slabs, you have to decide how you're going to build it. Are you going to build it with shear connectors to the flanges and make it act as a system, or are you going to leave them so that they can slide? So I looked at it both ways. I looked at it and said, okay, what if it slides? What if it's so sliding that it's so lubricated between those flanges and that concrete, there's no resistance to movement? What if there's friction between it? We looked at that. What if it's partially composite? What if it's totally composite? So all those, we neglected thermal expansion of the concrete slab, separated the connection modeling, missed web flange stiffeners were looked at. Okay, so all those issues is going on there. So our approach was to say, okay, let's take a structural modeling and look at two programs, the Abacus and the Sept 2000. We had established a quality control program by which we have two researchers. That was Zilli and Fong, and each one of them doing the same thing much of the time, and challenging each other with me there as a referee to make sure that what we got out of it was going to be, and if we didn't agree, we had dialogue. We would be able to try to find ways of what's going on here, what's wrong, until the point that scientifically we were able to justify every step of the way. Takes longer, but it's a value to make sure you have good stuff. So Abacus, we developed nonlinear springs for structural connections. What does that mean? It means that if you have these members bolted together and things move, and it moves fairly significantly, then it's probably not a linear curve. It's probably not straight line. It's probably going to deform non-linearly, and it may never come back the way it used to be. Okay? So we looked at a nonlinear response. We looked at composite, partial composite, and non-composite. We looked at floor 12 and 13, and we looked at thermal expansion. Sept 2000, we looked at floors 12 and 13 again, and floors 3 to 47. Here's what we did do though. We used the NIST fire models to look at this, and then we looked at heat transfer using SolidWorks, and we also used Abacus to do that. The steel framing, connection columns, and beams and girders were considered throughout the entire floor, not just part of it, by the way, not just part of it, all of it. So nonlinear springs on all stories is something we haven't finished yet, but we've looked at. Substructuring frames and concrete floor were used to minimize computer time. So it's my understanding that some of these computer models were taking up weeks to run. I went to a substructuring system where we could run them in less than an hour, maybe half an hour, maybe even less than that. I'm not sure. They ran really fast because I took out all the complexities and replaced them with equivalences. And then if we wanted to know what was going on within those equivalences, we put that stuff into those. So we could save huge amounts of computer time. Heat transfer was studied and we looked at the floor tile over the concrete with welded wire fabric, stay-in-place forms, flutes. So these were stay-in-place forms, by the way, and there's a flute. What does that mean? It means that there's a steel, I guess I don't know how to share that with you. Imagine if you take just a straight line and you drop it I guess a little square hole, you would say, and it's long. And so that space is a place where they don't put any concrete. It's an open space. Saves concrete, you still get strength, and that flutes. And so the question then became fire protection versus no fire protection. Okay, what does that mean in terms of fire? What does that mean? Is there an issue there? So we looked at that as well. We looked at equivalent concrete conductivity and expansion, counting for dolomite aggregate, welded wire fabric, and geometry of the section. What am I talking about there? Well, we went back to New York and we said, okay, what kind of aggregate are you using when you build this? And so we tried to be sure that we knew what aggregate, because the aggregate has a huge effect on the thermal conductivity and the thermal expansion of the concrete. It's 75% of the product. So therefore we need to know what it's going to be. And I had written a paper on this subject some years before and had a pretty good understanding of that. So this again is the NIST seat connection at column 79 that they did, but they didn't consider those stiffeners. So here's the way we begin to model the actual system, the way it went together. Here is those side plates. Notice that they're there. Here's the girder coming in. And there's the partial height stiffeners. And so therein lies, they actually were there, and we began to model this from a computer program to digital, so we knew how this thing is going to behave when you put it together. Here's what that floor system actually looks like. By the way, these are elevator shafts. This is over in here, is column 79. There's that there's column 44. There's that exterior of that floor. There's that whole system. All right? That's an abacus model, by the way, that we're looking at. UAF sample connection response. Basically, I'm taking every one of these connectors now. We've identified this and called it an STC. That's our name. STC, and what does it look like? It looks like this. That's the connection type. And we plotted the shear load versus displacement on it. So we can always go in and put that spring, wherever that's at, and get a response that will be equivalent to if we had used that complication, all of that complication there anyway. So we threw it away. That went away. We replaced it with an equivalent to save time. Then we looked at the fin connection, same idea. I'm going to not waste your time. That's how it was put together. There's how it's actually put together mathematically. That's what it starts looking like as a behavioral system. And then we plotted a curve for it, and we got a spring system out of it. Okay? Same idea. And so forth. So there's what it begins to look like. Basically, we put a load, we plot its behavior, and from that we can then put the equivalent into it. So this is a simple model of floors 3 to 47 from Sept 2000. And that's what we're using actually to look at progressive collapses with. So let's take a quick look at the materials that went into this thing, and I won't bore you too much, just a little bit. So the material properties: steel ASTM 572 was yield of 50,000 psi. Thermal conductivity of the steel was 35 BTUs per hour per degree Fahrenheit. Here's the thermal strain value. Density was about 490 pounds a cubic foot. We also had some ASTM 36 steels in here. I'm just not showing you all of it. Concrete's 28-day compressive strength was 3,500 psi. Density was about 145 pounds per cubic foot. Dolomite aggregate. We got a thermal conductivity from it. We got equivalent conductivity that we're going to be using here, and thermal expansion. So that's the kind of stuff that actually made up the model to simulate what we thought the building was going to be. We took and fixed the exterior column wall line here, as did NIST, and we subjected it to that heat up model, and we got very similar result. Well, we didn't actually. We did. This is not. I'm sorry. I apologize. This is not this is not the NIST model. This is our model. Here we have the connections as they truly are, all along this system, throughout this entire floor system, how it actually was built. Then we heat it up. And by heating it up, we have a dead load here of about 5,142 kips. We have a movement of that section right there of almost 2 inches, but not west. It went east. Totally different. The floor moved east at column 79, not west. And by the way, they moved together. They didn't move separately. So here's the material response versus temperature. Here's the column 79 column capacity curve as a function of temperature. So you can see even at, if you drop down into here, you don't get much change. The column 79, 392 degrees Fahrenheit. So this is load capacity versus the effective length for these various temperatures, okay? So this is 1832 degrees Fahrenheit. I think you can see it can make a difference. Huge amount, how much difference the capacity of that thing is. Okay, so let's talk about the fires that we actually put in this building, and here's what they were on floor 13. There's that whole area at 6 p.m., and then there's the fire, okay? And so that came from NIST, the NIST models, and we used them at this point. Same here on column 7, floor 12 and 13. UAF abacus structural expansive movements. Just kind of want to share with you. This is the model we're talking about. This is floor 13. This is the column 79 at floor 13, 1.85 inches to the right. That means east. That doesn't mean west. So this whole thing moved. I'll show you a different picture here, hopefully in a moment. So this is all this stuff to the east of this. So you can begin to see that the displacements, if you start looking at minus 0.50, in other words, where's the zero at? It's over here somewhere. So here's column 79. So it's moving with respect to this over in this area. It's not moving with respect to this. It's not moving with respect to that. It's moving this way and that way with respect to what we call the thermal centroid, which is your stiffer point. So basically you got a center of stiffness by which this thing is behaving. And that's what's happening here. So notice that our results in the Sept model, column 79, shows that we have 1.92 inches to the right. Abacus, this is Sept, 1.85 in abacus. We did it two different ways, got very close to the same answers. And then NIST is 5.5 inches to the left, revised to 6.2 inches. And why? Because of some of the things I was telling you. Understand? In my view. So let's do a little comparative game. Floor framing, steel connections. UAF accounted for them, NIST partially. We have exterior steel framing connections included springs. They did not. Exterior steel. I'm talking about the exterior walls. They had them fixed, remember? Floor is composite with beams and girders. I'm sorry, girder to column stiffener plates at column 79. Yes, no. What about the floor composite with beams and not girders? Both of us considered that. Composite with beams and girders. Yes, but they did not. Thermal expansion of concrete to the deck. Yes, but they did not. Thermal conductivity and expansion of material properties. So what I did is I went back and got the aggregate, then I changed it. I changed to make sure that we knew what the thermal conductivity of the concrete would be and the thermal expansion of that material if they actually made the concrete. Matched to the aggregate type. And so we accounted for that, they did not. Thermal horizontal movement at column 79 was less than 2 inches. Therefore, based on our analysis, column 79 temperatures were such that it did not buckle under any gravity loading. Couldn't have happened. So did the building 7 collapse from fires? No. This is based on our calcs. This contradicts the findings by the National Institute of Standards and Technology, the NIST approach. So that was what I view to be the real way it actually behaved, not what you assume, not what you do in terms of boundary conditions, making things perhaps easier for yourself or whatever. So the concrete floor diaphragm stiffness is significant, even with no shear connectors. Frictional resistance to thermal expansion is not trivial. We noticed that if you take out those shear connectors out, that they argue that they're not there. Take them out. I don't care. When they go away, I have enough friction and enough shear connectors on the beams that it doesn't matter. It's not gonna make a difference. So, that's what we determined, and we looked at it both ways. The thermal expansion of the concrete deck cannot be ignored, and it's likely less than the steel. The value is highly dependent on the type of aggregate. My research shows that you can have thermal expansion of concrete as low as 2 times to all the way to 12, whereas steel is about 6.5. So you know, depending on the aggregate. So we were dolomite aggregate, and so we matched to whatever we had there. The research team evaluated fire by considering airspace below the beams, in the space between the drop ceiling and the structural steel framing. We did that because a number of people felt like it was important. The result is that the fire underneath will likely burn through the drop ceiling quickly, and its resistance to heat transfer is likely not available to help. The NIST vertical collapse was not consistent with that of the actual collapse. I think I'm pointing out to you the progressive collapse picture that we looked at. That's what I'm saying here. You understand what I'm saying? When you look at it versus the structure, I don't think they look alike. Something's different, right? Totally different. I don't want that. I don't want that. That's not part of the game. So the NIST vertical collapse was not consistent with that of the actual. The difference was primarily influenced by not modeling a significant portion of the structural framing connection details. There may be other issues, but certainly that had an effect. There's no doubt about that. What's new? What's next? Well, we welcome your input. We welcome input from the world. We would want to be able to try to make sure that what our findings are based on scientific fact, and if there's a question, we're there to try to answer that and to make sure that our results are true and of value. We're providing the study to be peer reviewed. We are examining progressive collapse caused by various conditions, such as failure at the substation level, shock waves imposed by the falling debris from towers 1 and 2. What about the radiant heat that actually was imposed on the influence of that building structure by the towers 1 and 2 when they heated up under the planes? I'm interested in examining the building response for various columns being removed. We've already removed the inner core. I'm not sharing that with you, but it's very impressive what's going on. So then the question is what else is going on? And we're examining issues related to the perimeter trusses. There's been a lot of questions about what if they had a problem? What would that mean to this structure? So I think, folks, that I'm done. Thank you.
We'll take some questions. Yes, please.
I was just, you mentioned that NIST did model, for instance, the partial stiffeners and some of the shear connectors. Was there reasoning? Did they not find that in the wreckage and they don't think it was actually on the building? Or did they do that to make it easier to do the modeling?
I don't know the answer to that. I think it was an oversight. You know, I don't know how they got to that level, but I think it was an oversight. And so we're just trying to, I'm not here to criticize, I'm simply here to make sure that we did it the way the building was built. You know, try to answer that question as best we can. Yeah.
For the people online, I should probably give you the microphone.
Yeah, I guess I'm still a little bit unsure. When you said NIST revised their figure, they added an additional 3/4 of an inch or so of expansion. Maybe I missed it, or maybe you didn't touch it, but what exactly did they cite for revising that figure? Like, what was the variable they introduced that said, oh, hey, we were wrong, there was an extra 3/4 of expansion?
I'm not sure I know the answer to that either. I do know that initially they were using 11 inches as their measure on the base plate. Turns out it was 12. And so if it was 5.5, it would not have been a problem. So after some study, they came back and submitted a revision to that of 6.25, which would have been a problem.
All right, but there doesn't appear to have been like some new time, like where they said like 4 years later, oh, we've revised what we think the temperature is or the expansion coefficient itself. They kept all that the same, they just kind of said the distance was bigger?
They may have, I don't know the answer.
Okay.
Watch out.
I believe I saw that you had a note on one of the PowerPoints of the stiffeners that they were not shown in the shop drawings for the building. Were they shown in the as-built, or is it possible that those were left out of the police report because they did not actually end up getting installed in the building?
You know, Taylor, I don't know. I wish I knew some of those answers. I don't. I know that they're in the as-built. What we had are the erection drawings. And those erection drawings tell us how it was built. And so they might have had a different set of drawings without that. And there's a probability that's probably what happened, you know. And if that was the case, then they might have not had that information on it. But certainly the erection drawings showed it.
So, throughout the duration of your career, how many buildings of steel structures of this nature have you seen fail due to fire?
How about that many?
So, talking the changing situations in that case, were there any firefighting efforts occurring at that time, or were they all focused on WTC 1 and 2 rescue efforts? Because a lot of times you have additional water, supplies, and putting people in there that could place a large additional load. So you've already weakened theoretically fire conditions. Is there any knowledge as to how much water has flowed, if any, and where it would have gone?
I know there's been a lot of people that studied that a lot. And, you know, arguing, okay, there probably wasn't enough water to go around because of towers 1 and 2. This is many hours later. You know, that thing was sprinkled also. It was also had fireproofing on it. Question is and the other question you have to ask yourself is, you know, I have another slide here. I'm sorry to say I didn't see it when I just put this together a few minutes ago. I mean, going through it, showing at every floor what kind of activity was going on. And it was almost all financial. So one has to ask yourselves, I don't believe people's investment portfolios would be out on the tables. I think they'd be locked in safe. So how much paper was out there? I just don't see where there was a lot of combustibility going on with that structure. So to be on fire for 7 hours, which is over that period of time, probably not very high temperatures, you know, were developed. And that in that period of time, now I don't know this to be the truth, but I'm told that 2 o'clock in the afternoon, the fire department left and said it was not a problem, and yet that later it happened. So that's a bit disturbing in itself. So I'm not here to, you know, to try to guess at where people were with all these issues. They had their hands full that day. That's for sure. Okay.
So 2 more questions relating to the fire. Number 1, do we have any clues as to how the fire actually started, what occurred that caused the fire? And the second question is, do we know what it was that was burning for the majority of that time?
Well, there's almost all of it's reported that almost all of it started by the debris falling off of the tower number 1 and going through the windows and causing all that kind of damage. And so that then caused the fires, and from there they were burning.
If I remember correctly, when the planes first hit towers 1 and 2, there was fly-through debris that actually hit tower 7. Have you looked at what kind of damage would be caused by the fly-through debris, and what columns or girders would have been taken out so that it would have weakened the structure inherently in a different aspect?
There's quite a bit of work that's been done on that issue, and there was some damage, but structurally, most people argue that it just wasn't that significant. So yes, there was fires, but the damage to the structural columns were not that bad. We did look at some of that damage.
Great questions. Any more questions or comments?
The thing is too is, you use the terminology progressive collapse. Is that, when you say that as an engineer, do you mean the same
Well, that's a progressive collapse phenomenon.
Could you repeat the question?
Yeah. So the question is what he was wondering to know is what, in engineering terms, what is a progressive collapse? I think that's an accurate question, what you're asking, right? And does a pancake qualify for that? Okay. So progressive collapse means that, okay, there's something starts, and it gets progressively worse and worse and worse and worse, and that leads to the failure. So as an example, when they came out with the theory that the failures of towers 1 and 2 were caused by pancaking, where the floor bang, 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 bang. That's a progressive collapse. It doesn't happen immediately. It's not like that. There's things going on, and it's ultimately leading to things getting worse. What we looked at in that video was a progressive collapse. It started, and it was going down. And there's a physicist that actually plotted that, and that's free fall.
Yeah, because I wanted to have a follow-up question. I think you already kind of getting partially on is that the rate of acceleration as it's going down, the video implies that there's little to no resistance impinging against the acceleration. But your modeling, and even this modeling, would imply that, you know, you're going to have an initial force hitting more and more mass down below it. You would think that would be
Well,
removing velocity.
So repeat the question.
okay. So the question I guess you're asking again is about the free fall versus the NIST model showing that it wasn't, you know, it was moving down at a slower pace. Is that accurate what you're talking about?
Yeah.
Okay.
Yeah,
So if you look at that, no, we didn't show you our progressive collapse, by the way.
exactly. Right.
We're not going to do that until we're sure that what we've got. But we do believe that we're getting close. Now, the point is that what the physicist did is he took that video and he put it against as a function of time. Took every one of those blocks, and he has the rate, and from that he plotted it, and that was free fall. That's the real structure, not the NIST structure. Okay. And so, and we only see a part of that building. We don't know what's going down under floor 29. We have no idea what's down there because we can't see it, right? So that's where we're going to be. I mean, we're spending a lot of time trying to see what is going to happen there. But in order to get free fall, that means you have no resistance. So it leads you somewhere, right? Something to think about that. And if you have any elements of the structure that are resisting load, you have resistance. So you're not going to get the same time frame, no matter how much load you dump at it, in terms of how it's failing, unless there's nothing there to resist it. Okay.
So, what structural failure conditions would you need to get free fall?
Well, it means you don't have any column support and you basically have no column support to carry it. So it comes out at a point in time where they're all coming out at the same time.
So how does that happen in the real world?
I'm going to let you have an imagination about that.
So in your analysis, you only found less than a 2-inch movement at column 79, right? So was that due to the exterior wall actually moving out, or was it another part of the building that was moving at the same time, or was there just not as much displacement?
Okay, so here's the thing. When you take a look at the building movement as a result of heating up that floor, same heating up that they did versus me. If you look at what's going on there, column 79 moved about almost 2 inches, 1.92 versus 1.85. That's almost 2. The exterior wall moved almost 6. The movement of point 0 was way to the west of column 79. So the floor was moving with respect to a center point that is not what they, okay, so when I say column 79, I'm not saying column 79 moved some amount and the girder moved a different amount. They both moved the same at that point. So there wasn't any, I mean, that's sliding around is going to happen. I mean, that issue is not the same. The way you're going to get the movement of going to the west is to lock the exterior wall and lock the columns so they can't move. That means everything's got to be shoved. How do you do that? It's not what's there. So that means you got to give it an artificial constraint. It's the only way it can happen.
So is it possible that the NIST report had that wrong because they only modeled half of the building or less than half of the building?
Well, that was part of that. That was part of the picture, for sure. But the only modeling part of it is also another problem, right? And then, and in addition to the other things I brought up, yeah, there was a number of factors.
So, like, I know in structural engineering, you tend to discount the facade, the glass that's still on the outside, because you really don't want to be able to take a window out and not have a building fall down. But I'm wondering, in a situation like this, if the extra stiffness of having all the glass and the stone on the outside, if that did produce more blocking out there.
I don't think so. But I think a more compelling thing for you to think about is when you look at that video, and you can go on YouTube, you can go on the internet, and you can see it all day long. Take a look at it. And you will see, tell me how many stress points do you see on that exterior skin? It's very thin. It's not a load-carrying system. And you don't see any deformation, you don't see any racking, you don't see any of that kind of stuff going on.
It's surprising how strong the facade looks like. You can see the stone.
Yeah.
That's the first thing, and then apparently the outside of the building is just standing there for at least a few seconds till the bottom gets taken out.
It's kind of exciting, isn't it?
It's a very dramatic event.
Okay, well, Professor Hulsey, thank you very much. It was very interesting. Appreciate your presentation and your analysis. Look
Thank
forward to seeing the full report.
Okay, thank you. Thank you. Thanks.
Good questions, too.
Yeah.